I want to talk about some examples of varieties satisfying the multiplicative Chow-Kunneth decomposition. But before we get there, let's review things we know. So our object of interest is Chow rings. So I am guessing that most people have seen Chow rings in some form. So I'm not very sure about this. So I want to be able to see the participants more, but okay. Anyway, so our object of interest is Chow rings. So if we start off with, let's say, X, a smooth projective variety of dimension n, we recall that the group of algebraic K-cycles, ZKX, is the free abelian group generated by irreducible codimension K subvarieties. Okay, so K subvarieties of codimension K subvarieties of X. Okay. So an element in ZKX is called an algebraic K-cycle. So, every time we hear this word, this is what you should think of, is that the element alpha looks like a formal linear combination of irreducible codimension K subvarieties of X, meaning it's N1, Z1 plus blah, 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 to let's say NP, ZP, with the Ni's integers and Zi's being irreducible codimension K subvarieties. Okay, so I believe that everybody is a little bit used to this already. But okay, so the thing that is very important is this equivalence relation on this free abelian group. And the equivalence relation is called rational equivalence. So what is rational equivalence? Okay, so suppose we have W, an irreducible subvariety of X cross P1, not contained in a fiber. That means there is no T in P1 such that W is basically just X cross T. Okay, so here we have X cross P1 and W is an irreducible subvariety in there, but it is not contained in a fiber. Okay, now we say that two irreducible subvarieties Y0 and Y infinity in this ZKX, so two irreducible subvarieties of codimension K of X are rationally equivalent if we can write Y0 as W intersect X, the fiber of X over the point 0, and Y infinity as W intersect the fiber of X over the point infinity. Is this clear? Hello?
Yes.
Okay, so am I losing people or they're just...
No, it's good, all good.
Good. Okay, so the thing is I'm not able to figure out how to see people, but okay. So the thing is that, I could have drawn a picture here and, that might be helpful. But on the other hand, sometimes my drawings are not very illuminating. They actually are confusing, but you can, use this to draw a picture and see what this means. So what you basically say is that you can interpolate between Y0 and Y infinity. Okay, so this is the meaning of rationally equivalent. So the Chow group, CHK of X, is basically just the group of algebraic K-cycles modulo rational equivalence. Okay. Now here what I have done so far is that I have considered codimension, but I could have equally considered dimension. If I did that, then CHKX would just have been CHN minus KX for n equals the dimension. Okay, so when I'm considering dimension, we put the index at the bottom, and when we are considering codimension, we put it at the top. Okay, and throughout this talk, I will be considering codimension. So it will be CHK, this will be algebraic cycles of K algebraic cycles. Okay, so codimension K, formal linear combinations of codimension K subvarieties. Okay, so CH0X, so that's when, it's the codimension 0 cycles. Well, this is just freely generated by X. That should be easy to see. CH1X, so codimension 1 subvarieties. Well, we know that this is the divisor class group, okay, and we know that we can think of this divisor class group. So here I am always in the smooth setting, okay. So I can think of this as the Picard, the group of the Boolean group of line bundles on X, okay. And then it's not very, also we know that it's not hard to see that if you were to consider codimension greater than the dimension of X, then obviously the kth Chow group will just be 0, right? I mean, that's tautological. So, okay. So if you have never seen Chow groups before, and I know that every time I start talking about these kind of things, people, I mean, it's not new. As I said, we've all worked with Chow 1, but still somehow this seems a bit too, different. People think that it's a bit weird, this rational equivalence business. So if you're a PhD student or you're not used to this and you're getting really bored while I'm, going on about definitions and definitions, then here are some exercises for you. That the K Chow group of the affine space is 0 for all k except k equals 0. Okay, so only the Chow 0 is non-zero, but all the rest. So for example, Chow 1, which we know is isomorphic to pic x. Why is that? Why is that 0? So this is a good exercise for you to try if you've never seen these things before. By the way, this is also there in Hartshorn as a proposition, but yeah, I recommend you actually try this. Okay, now if we take projective n space, Pn, and we let L to be a codimension 1 linear subspace, then actually we can say that the Chow k of Pn is freely generated by L to the k. Okay, so again, this is an exercise. You should see why this is true and what is this canonical choice of L that you would take. So these are good exercises, but this is a little bit maybe misleading, because you see here I'm telling you that you can compute the Chow groups of the affine space and the projective space, and this is correct. But actually, if you were to just consider some arbitrary smooth projective variety, then to compute the Chow, the kth Chow groups for k greater than or equal to 2 up until the dimension of X is generally huge and mysterious. So this you cannot actually compute them. It's next to impossible. Okay, so so one should actually try these things, because we know Chow 1, right? That's just pic x. Okay, so this is divisor class group, which is isomorphic to pic x. But as soon as we get to Chow 2 onwards, it gets really hard. So these two are the kind of examples which are easy. Okay, so what have we done so far? We have covered what are Chow groups. Now there is another very important ingredient. It's called the cycle class map. Okay, so what is the cycle class map? So again, to define this, suppose I have a variety, a smooth subvariety of codimension k in X. Okay, it has an inclusion morphism I can take the push forward. So this is homology. Okay, so I can take the push forward in homology, because I don't have a push forward in cohomology, but I have a push forward in homology. So I can take the push forward in homology of H2n minus 2k of V, the homology group of V, to H2n minus 2k of the homology group of X. Okay, and what does this do? So it takes, this is a group, it has 1, and the image of 1 is what I call the fundamental class of V. Okay, so this is the homology group of V, and the image of 1 under this map is what I will call the fundamental class of V. Okay, so now I know that X is smooth, so by Poincare duality, I can go from homology to cohomology, but of course then the indices change. That's fine. So I have that H2n minus 2k, the homology group, is isomorphic to H2k, the cohomology group H2k. Okay. Okay. So this is what I did when the variety, the subvariety was smooth. But of course, X could have singular subvarieties. So what do I do if it is singular? V is singular. I just basically resolve and repeat. Okay. So what have I done? So what I'm saying is that for any subvariety, smooth or singular, of X, I can map it from. So it is going to be an element here in the group of K algebraic cycles. Okay. And I can map V to its fundamental class. So I have a clearly well-defined image of V. And of course, any element here, any algebraic K cycle, is just a formal linear combination, right, of irreducible subvarieties of X. So I can use linearity to then give a good definition of what I mean by the image of algebraic K cycle under this cycle class map. Okay, so it takes an algebraic K cycle and it spits out a class in cohomology. So just to be clear, all the cohomology groups here are singular cohomology. Okay. Okay, but as we have just seen, if we just mod out the group of algebraic K cycles by rational equivalence, we get the kth Chow group, right? So essentially, we have the cycle class map is giving us a map from the kth Chow group to H2K of X. Okay, so we have from the Chow group to the cohomology group. So this is the purpose of the cycle class map. And maybe just to be a bit interactive and make sure that people haven't fallen asleep. So can anybody tell me if this map is going to be, you know, if you know of any interesting conjecture related to this map? Okay, so the Hodge conjecture, which I sometimes give talks about as well, is related to this map. But okay, so so far what we have done is we have defined what are Chow groups. We have discussed what is the cycle class map. Now we have something else called the intersection product, which is an intersection product on the Chow groups. So basically, if I look at CHR X and CHSX, then I can define a product here such that I take an element alpha, so an algebraic R cycle. I take an algebraic S cycle, so these are two rational equivalents, and I can get an element which is going to be an algebraic R plus S cycle. And so I go into the Chow group of Chow group R plus S. And how does this work? What is this intersection here? What is this product? So just to again make life simpler, I will start with what happens when, you know, alpha and beta are just some varieties, right? So instead of just thinking of them as formal linear combinations, when I'm thinking of them as cycles, just for simplicity, I start with them as just being some subvarieties, V and W, okay? And then I can just proceed by linearity to define this for the cycles. So for V and W, subvarieties meeting subvarieties in X meeting properly, what does it mean to meet properly? It means that the codimension of V intersect W in X is equal to the codimension of V in X plus the codimension of W in X. Okay, so this is when this happens, I say that V and W are meeting properly. So if I have that V and W are meeting properly, then I can take this intersection. So I can take this operation V dot W to just be literally the intersection of V and W with multiplicity. Okay, and So the multiplicity is denoted by m. And I say that m is equal to 1 if and only if v and w intersect transversally. So intersecting transversally is a condition kind of on the tangent spaces. So that means that for every point P in the intersection, the tangent space of V at P and the tangent space of W at P is equal to the tangent space of X at P. Okay. So in particular, both V and W are smooth at the generic point of every irreducible component of V intersect W. Okay, so this is what it means to intersect transversally. And then there is a very important result called Chow's moving lemma, which tells us that actually we can always find representatives for V and W. So here, we said we defined this product, right, for when things are intersecting transversally and when they're meeting properly. So the question is that can we always get this situation? And yes, we can. So Chow's moving lemma tells us that we can always find representatives for V and W such that they intersect transversally. Okay, so now we come to our object of interest, which is the Chow ring. So just to be clear, I kind of started 5 minutes past or something. So do I have up until, how long are the talks?
Usually it's a total of an hour, so you can until
okay.
5 past.
Okay, good.
Give just if you can give some time for questions and stuff.
Yes.
But yeah.
Yes. Okay, good. Yeah, so because I have a lot of things to cover and I'm seeing that the time is going quite fast. But okay, so as I said, also if I'm kind of reviewing things that I think everybody has seen, maybe do not work with, but they have seen this. So, but yeah, so it's a little bit maybe fast. But if you have any questions, please feel free to stop me.
Yeah.
So now,
can I ask?
Yes.
Sorry. When you say you have the multiplicity is 1 when this condition happens, but what other type of multiplicity you have? Are they usually bigger than 1 or smaller than?
Yes.
Because I'm not bigger than 1. Then.
I mean,
okay. Yeah.
So I can have m to be greater than or equal to 1.
Okay.
So it can be more than 1. Yes.
Okay, and it will be if you have singularities or something, or what will make this multiplicity to increase?
No, so here is the thing. I want that V and W are smooth at the generic points, and this is kind of
Okay,
so
that's
this is
always the case. Okay.
Yes. Thank you. That's good. Okay, so yeah, I think maybe this is better than the slideshow for going up and down. So the Chow ring. So far, what I've done is that I have defined Chow groups. Yes. And the Chow ring is basically just taking the sum of all these Chow groups. And the thing is that it's a ring, right? So ring means that each of these groups was a billion groups, right? We were just taking ZKX and modding out by rational equivalence. But the sum here, the direct sum, is actually a ring. Okay, so it's a ring Y. And what is the multiplicative structure? Well, the multiplication is given exactly by what I just defined by the intersection product. Okay, so that gives a multiplication on this ring, and it makes it into a graded ring. Yes, graded by codimension. So as we can see, we land, right, CHRX times CHSX lands in CHR plus S of X. And so this property makes it into a graded ring. Okay, so it's graded by codimension. Okay, so so I hope this is clear so far. So here is a question: are there varieties, say X, such that the Chow ring is not just a graded ring, so this by codimension, but it is actually a bigraded ring? What do I mean by a bigraded ring? I mean that I have, instead of just indexing by K, the codimension of the Chow groups, right? Sorry, the codimension of the cycles. I have that. I've got another index S, so that I can write this as CHKXS. Okay, so I'm taking two gradings for some appropriately defined Chow K X little s. So we have a grading. Now what we are asking is if we have a bi-grading. Okay, so I mean I will make it more precise in a minute. But the answer to this question was given by Vial long ago, and it was yes. Okay, so what he said, in order to say that, I need another definition. So X is a smooth projective variety over C. We say that the Chow ring admits a multiplicative splitting. So here, again, we are just giving a property of the Chow ring. We say that it admits a multiplicative splitting if the following hold. One, I can write this as the Chow K X, exactly this bi-grading property. So there is a decomposition. And again, I have a multiplicativity property. So far what I had with the intersection product, right, was that I just had Chow K X times Chow K prime, and it was ending up in Chow K plus K prime. Yes, this is what I had in the intersection product. Okay, but now what I'm saying is that I want something a little bit stronger when I have multiplicative splitting. I already have this from the structure of the Chow ring, but I actually want also this other grading to have this multiplicativity property. So that means I have, let's say, this grading J, and then I have J prime, and this ends up in not just Chow K plus K prime of X, but actually in Chow K plus K prime of X, J plus J prime. Okay. So obviously this is a very strong condition, right? That you will have such a multiplicative splitting. And the thing is that the reason why this definition came up is that Vial showed that actually if I take an abelian variety A of dimension G, then I can write down each of the Chow K, the K Chow groups of A as direct sum of, so I'm now decomposing each of the K Chow groups, okay, by this other index J. So I can write this as a sum of Chow K A J, and J goes from K minus G to K, okay. So what are these? Well, he gave very explicit definition for what these are. These are looking at all the cycles in Chow K A such that when so I'm in an abelian variety, I have the translation map. So when I pull back via the translation map, I just get that the pullback of the cycle alpha, let's say alpha in CHKA, is m to the 2k minus j alpha for all m in Z. Okay. So this is a very explicit form. So what have I done? I was decomposing first. I had this. I was looking at the Chow ring as a direct sum of all these Chow groups. But now Vial is saying that if I have A an abelian variety, then actually I can look at the K Chow groups of A as some direct sum of as graded by this Chow K AJ. Okay, and so I have a bi-grading. Yes, on the Chow ring, because on each of the Chow groups I have a grading. Okay, so the question is, what class of varieties can we expect such a splitting from? So clearly he showed this for abelian varieties, but are there other varieties that might also have this kind of, splitting? And so if you get lost during my talk, one of the themes of the talk really is trying to answer this question, okay? So I'm going to give lots more definitions, but essentially it's going to get related to this question of Vial. So in order to get to examples where this holds, I need another theory called correspondences. So I'm guessing that people haven't seen correspondences before much, even if they have seen Chow groups, unless you're really working with Chow groups, you maybe heard of it, maybe not. So what are correspondences?
So wait, sorry, are you saying you need this splitting for bigrading? Or are you just saying this is the specific case for the abelian?
No, this is just in the abelian case. Okay, so what I'm saying is that the concept is not just, let's go and cook something up. It does exist, so that's why then we try to generalize it, right? So this is the basic thing in maths, that we have something works for, let's say, a certain variety. We are very happy with it. We study that variety. We find some phenomena. Then we say, well, forget about this variety. We are more interested now in the phenomena itself. So what other varieties exhibit this phenomena? So you have this with, for example, Mori dream spaces, right? You have toric varieties are Mori dream spaces, but then at some point you found this and you got so excited about the concept of Mori dream spaces that you start asking what other varieties, forget about toric varieties, have this property. So in some sense, this is what you're doing. You notice this for abelian varieties, and now you ask what other varieties could have this. Okay, so in order to define these things and give some examples, what I need is the theory of correspondences. So as I said, so a correspondence between, so I have X, Y, and sometimes I'll need Z. So smooth projective varieties, okay, they're all smooth projective. A correspondence between X and Y is a class gamma in CHK of X cross Y. Okay, so that should not be very surprising. So basically, I'm just saying I'm taking the class of an algebraic cycle, algebraic K cycle, modular rational equivalence. So, okay, I could do this for just CHK X. Now I'm doing it for CHK X cross Y. Okay, so it doesn't seem anything strange. So I'm just thinking of this as a subvariety, if you in the simplest case, if you like. But here's the thing. I am now kind of thinking of cycles, algebraic K cycles, as having a dual property, if you like. One, I can think of them as just this formal linear combinations of irreducible subvarieties mod rational equivalence. This is what I've done so far. But I can also start thinking of them as maps. Okay, I can think of them as maps from X to Y if I am looking at them as algebraic cycles in X cross Y. So this is basically what a correspondence is. So I can think of the set of all correspondences as just the Chow ring of X cross Y. Okay, nothing too deep there. I've said that a correspondence was just a class. But here is the thing. I can actually compose correspondences. Okay, what does that mean? It means that if I take a correspondence gamma in, sorry, I have a bit of a hay fever, so if I have a correspondence gamma between X and Y, and I have another correspondence beta between Y and Z, then I can compose gamma with beta, okay, to get a correspondence from X to Z. So how do I do that? I do it as follows. I have my beta, which is a correspondence from Y to Z, right? So this is a correspondence between Y to Z. I pull it back via the projection map, YZ. So what was YZ? So I have X cross Y cross Z, and I project to Y cross Z. Okay, so I pull back my, so I have my my class here, beta, right? A correspondence is just a class. I pull it back, and now I'm in this Chow ring where I have intersection, right? So if I also take gamma and I pull it back via the projection map XY, so gamma is a correspondence between X and Y, and I have this projection map x cross y cross z to x cross y. I can pull back gamma. So again, I have now an element in the Chow ring x cross y cross z, right? So what I can do is I can do intersection, right? I mean this I have the intersection product here. Okay, so I intersect, and then what? Well, then I have the projection map xz, which is going from x cross y cross z to xz, and I can push forward this intersection, this class, right? And I get a class in x cross z, right? In the Chow group of x cross z. So essentially, I get a correspondence between x and z. Is this clear? Because this is a little bit technical. So yes. I have these maps, and I know that I have a correspondence. Is just, you know, I have a class in the Chow group. I'm pulling it back via these maps, and then I am sitting inside the Chow group of x cross y cross z, the Chow ring of x cross y cross z. There I have the intersection product. I intersect, and then again I have this projection map. I push forward the class I have gotten to get a class in the Chow group of x cross z. Okay, so good. So here I am thinking of this really as, you know, I have my algebraic cycles. But what else I can do is that I can think of gamma as giving me a map. Okay. And how do I get that? I can get a map between, let's say, the singular cohomology groups of x and y using gamma. So I told you in the beginning that I have the cycle class map, which goes from the Chow group to the singular cohomology group, right? So if I have gamma a correspondence between x and y, so basically it is just a class in here, then I know that I can take the image of gamma under the cycle class map, and this will define a map between the singular cohomology groups of x and y. So, sorry. So, if I have m is the dimension of x and m is the dimension of y, then we have that I can use the image of the correspondence gamma under the cycle class map. I can use it to get a map. So the push forward of that gives me a map from the singular cohomology of x to the singular cohomology of y. Obviously here, as you can see, the indices look a bit weird. What's going on? But again, it's exactly what we had for the cycle class map thing, right? We don't have a push forward on cohomology. So what we have to do is we go to the we do Poincare duality to go to homology, then do the push forward, then do Poincare duality again, and that kind of gives us this weird change of indices. Okay. Okay, so how does this work? So basically, if you take element alpha in HKX, then you can do the following. You can pull back alpha via the projection map. Okay. You can cup it with the image of the gamma under the cycle class map. So the image of gamma under the cycle class map lands in a cohomology group, right? That's what it was. So the cycle class map was taking things from the ZKX to the cohomology H2KX or whatever. So I have that, and there in cohomology I have this cup product. So I do that, and then again I push forward with the projection map PY. Yes. And that gives me an element in the cohomology group of Y. Okay, so the purpose here is that what I'm trying to do with these things, and I know they are kind of hard to follow online, is that I'm trying to tell you is that I can think of algebraic cycles, right, as just cycles. These are just formal linear combination of irreducible subvarieties, let's say modular rational equivalents. But I can also think of them as maps. Okay, so essentially correspondences are a generalization of regular maps between varieties. So if you're thinking, how? Well, let's say you have a regular map f going from x to y, yeah, x and y, some smooth projective varieties. If you look at the graph of f, right, gamma, the graph of f will give you a correspondence. Okay, and this kind of thing that you're doing, the push forward and pull back with the correspondence, will just be the pull back and push forward of the morphism f that you have. Okay, so what I'm trying to say is that it looks a bit weird, but it's not. You're thinking of this class as an element in Chow K x, in Chow K x cross y. You can also think of this as a map, okay, from x to y. Okay, so what happens? So here I use these indices x and y. I use these symbols, but most of the time we will really be dealing with self-correspondences. So what are self-correspondences? So gamma is a self-correspondence if y equals x. So it is just a cycle, a K cycle in modular rational equivalence of x cross x. Okay. So are there any questions so far? Okay, that's good. So a Chow-Kunneth decomposition for a variety x of dimension n. So we know now what are correspondences. We also know what are self-correspondences. These are just when y equals x in the above definition. So a Chow-Kunneth decomposition is a system of self-correspondences going from pi 0, pi 1, pi 2 up until pi to the 2 times n, where n is the dimension of x. Okay, and so all of these are going to be self-correspondences in CHN x cross x. So here, just to be a little bit careful, okay, this pi 0, pi 1, it is not that I have the same self-correspondence pi and I'm just taking powers of that, or just composing it the way I was composing it here, right? So this is kind of an easy thing to think of, that maybe that's what you're doing. No, that's not what I'm doing. So I could have just put these indices at the bottom, on the bottom, but the issue is that there will be a lot of things on the bottom, so you put it up, okay? But do not think that this is composing pi 1 times, 0 times up until 2n times. No, it's not. And why? Because the first thing is that if you compose, let's say, any of these pi i's, okay, with themselves, pi I, then you just get pi I. Okay, so this property that you compose any self-correspondence with itself gives you the self-correspondence again. This is what you call a projector. Okay, and then the other property that this system has is that if you take any 2 ij's distinct and you compose them, as we've been composing correspondences, you just get 0. The third property you have is that you know that you have this diagonal, right, of x, which is just x comma x in x cross x. So here you can really think of the diagonal is certainly going to be a class in CHN x cross x. So this diagonal can be written as a sum of all these self-correspondences in the system. Yes, so this self-correspondences, the sum of this gives you a decomposition of the diagonal. Okay, and then fourth property that this self-correspondence system should have is the Kunneth property. So what is the Kunneth property? So this tells you that if I look at the push forward of the correspondence, any correspondence by I, any I, if I do the push forward of this on the cohomology ring of X, I just get back HIX. Okay, so what do I mean by using a self correspondence to give me this kind of push forward? It's exactly what I just defined before, that I know that I can take the image of this correspondence under the cycle class map, and then I can do a push forward, and this is exactly what I'm doing here, except that Y is equal to X. Okay, so it's a self correspondence.
Sorry, can I ask a quick question?
Yes.
Maybe you mentioned before, but I didn't catch it. Why do you have two n self correspondence?
This is a good question. So I have so N is the so the Chow group, right? So what is the dimension of X cross X if the dimension of X is N?
2n.
Exactly.
Okay.
Okay, so that's what it's coming from. Good, very good. Yes, so it will always be that. And this property is that you really need 2n plus one of these to give you the diagonal. Okay, if you take the sum of these. So here you have n cross n, so you have 2n. Okay. Okay, so as you can see, this is kind of looks like, so here we are not saying that every variety has a Chow-Kunneth decomposition. That is Murray's conjecture that any smooth projective variety has a Chow-Kunneth decomposition. Okay, and it is still open. So we do not know a priori still if a smooth projective variety has a Chow-Kunneth decomposition. So in order to get a Chow-Kunneth decomposition, I need this system of self-correspondences. Okay, satisfying these properties, which are quite technical. And so the definition by Shen Vial is that actually you can go a step further. And this is where we are going to relate things to what we had in the beginning with Beauville. So you can say that a Chow-Kunneth decomposition is multiplicative, okay, if the following thing happens. You take pi I tensored with pi j. Okay, so this is, again, I didn't quite define what is a tensor here, but it is very similar to the, what we did with the composition, except that we need more factors. So it's if the projection maps look more complicated. So we take a tensor of any of these two self-correspondences, okay, and then we compose it. We know how to compose correspondences, so we compose it with the class of the small diagonal. So this is again a self-correspondence. So what is the small diagonal here? So the diagonal we had is just x comma x, right? But the small diagonal is x comma x comma x in x cubed. So here we are really in x times x, okay? And then when we compose this with pi k, so k should not be equal to the sum of I and j that we have taken. Then this, if this is equal to 0 in the 2n Chow group of x cross x, we say that the Chow-Kunneth decomposition is multiplicative. Okay, so first we need to have this Chow-Kunneth decomposition. Then we need to show that it satisfies this property for any ijk. Okay, then we know that the Chow-Kunneth decomposition is multiplicative. Okay, so what is the purpose of coming up with such a complicated definition? I mean, it looks like, why would you want this? Well, the key implication is that if you have a multiplicative Chow-Kunneth decomposition, then this induces a multiplicative bigrading on the Chow ring. So you remember the question of Beauville was that when can we have this bigrading? So he was asking more like the multiplicative splitting, but okay, you know, when can we have a bigrading on the Chow ring? And one of the things that Shen Vial tells you is that if the Chow-Kunneth decomposition is multiplicative, then you have a bigrading on the Chow ring. Okay, so now, but this is a little bit stronger, if you like, than, you know, just the splitting thing. But the point is that, of course, if a variety has this, then it has Boville splitting. Okay. So basically what you're saying is that you can write your Chow ring as Chow IX, and here you're going, sorry, I should have put an S, I have missed an S here. Where the Chow IXS is basically just the push forward of the, under the correspondence 2I minus S of the Chow, Chow I of X, okay? So I don't know if this is making much sense, but essentially what you're doing is that now you're looking at your, you know, this gives you a way because of this property, right? You had this Kunneth property, which was telling you how to go from the cohomology ring of X to the cohomological groups. Each of these correspondences, when you're doing the push forward, you are doing something to the Chow groups, right? So obviously you can define Chow IX little s in this way, and if you can, then you can write each of the Chow IX as a sum of these Chow IX S's, and so you get a grading, a bigrading. So one, you had the grading from codimension, but now for each of the codimensions, you have this other degree grading going on, and so you do get a bigrading on the Chow ring, which respects the multiplication. Okay, so first of all, are there any examples of things that have this other than what, you know, Boville's abelian varieties? And yes, okay. So if we look at curves, P1 actually has multiplicative Chow-Kunneth decomposition. It's not too hard to show, but it is still technical, so I did not write it down. Elliptic curves, so these are just, you know, dimension 1 abelian varieties. So again, by Boville's theorem itself, they have elliptic, MCK. Hyperelliptic curves, this is harder to show. This is a result by Gross-Shen, also admit MCK. And so there are lots of things that do admit MCK, but here is the thing. Unlike this having a Chow-Kunneth decomposition, which is Murray's conjecture, having a multiplicative Chow-Kunneth decomposition is a very strong condition, okay? So this property is actually very strong. So there are lots of even curves that do not have MCK. So a very general curve of genus G greater than or equal to 3 does not have MCK. Now, if we go into the case of surfaces, abelian surfaces, because abelian varieties have MCK, abelian surfaces have MCK. Projective K3 surfaces have MCK, and this is a result by Boville and Voisin. But again, a very general surface, S in P3 of degree very large, does not have MCK. Okay, and this is a result by Kieran O'Grady. So the other thing is you can ask is that is MCK unique? Like, are you going to have, you know, this unique set of self-correspondences which have these properties and then, you know, have this property as well? And the answer is no. Okay. However, the important part that we were looking for, right, is that whether it's going to have a bigrading on the Chow ring. It's going to give us a bigrading on the Chow ring. And yes, as soon as you have a 1 MCK, you have a bigrading on the Chow ring. And if you have any other MCK, right, that will still give you the same bigrading. So the bigrading is going to be unique. Okay, so here is the conjecture of Shen Vial, which seems like it's a little bit harder in some sense because MCK is a very strong property. But they say that any hyperkaehler variety admits MCK. Okay, so Beauville formulated a conjecture which said that any hyperkaehler variety will admit this splitting of the Chow ring, but that is kind of still a little bit weaker than having MCK, because MCK has this very strong multiplicative property, right? This is the point of it. And Shen Vial say that actually any hyperkaehler variety should admit an MCK. So what is a hyperkaehler variety again? Well, a variety X is called hyperkaehler if it is simply connected. And you know that H0 of the omega 2x is just going to be generated by a everywhere non-degenerate holomorphic 2. Okay. And the thing that you know about hyperkaehler varieties is that as such, we just have a kind of finite set, right? I mean, there are, of course, many deformation families, but we have a finite set so far of the hyperkaehler varieties that we know. We don't know many. So we have K3 surfaces, we have Hilbert scheme of endpoints, we have generalized Kummer, then we have the O'Grady sextic and the O'Grady 10. And so, I mean, in order to really verify this conjecture, what you have to do is go through each one, you know. So Voisin already proved it for K3 surfaces. The Hilbert scheme of endpoints was shown by Shen Vial, and also the generalized Kummer varieties have been shown. But in general, we have not finished the conjecture yet because it is hard to show what the candidates for these self-correspondences should be. Okay, so one of the things is that when you have curves, right? So coming back to Roche's question, right? So Roche, if you have a curve, how many self-correspondences do you need? Hello.
So sorry. Then will be 3, no?
Exactly.
Right.
Exactly. And there is, I did not write this down, but there is a canonical choice for the first and second, I mean the first and last. So you basically just need one in the middle. So that's not so bad. Okay, you can find that. If you have a surface, how many would you need? 5?
5, yeah.
Okay, so again, you know the first and last, you have to find some in the middle, not so bad. Okay. But you can see that if you go higher and higher in dimension, this gets very hard. So actually, this is one of the problems. Okay, so it is very hard to know what are good candidates for, because you need the system, right? You need, like in the case of surfaces itself, now you need 5. So curves is the easiest to show. Okay, so if you do something of dimension 10, you need a lot of these self-correspondences. Okay, so that's why the higher dimension hyperkaehler varieties is kind of hard to tackle. Okay, so what am I trying to do? So I don't know how much time I'm going to have now. I'll probably have just 5 minutes. But so the thing that I'm trying to understand with Robert Laterveer is that we know that there are things that have hyperkaehler. We also know that there are things that don't have, there are things that have MCK and there are things that do not have MCK, right? Even for the case of curves. Again, for the case of surfaces, we have examples, we have non-examples. So the question is, what is the boundary? At what point will you stop having MCK? Like how do you, try to understand when things start to go wrong? Okay, so this is one of the things that we are trying to look at. So our first result is a kind of a positive result, but before I can define, give details, I need more definitions. So I think that everybody probably has seen Hilbert scheme of points. So this is a very general definition. So if you take X to be a smooth projective surface, so of course it need in the general definition, you don't need projective and you don't need it to be a surface. It could be quasi-projective and you could just have any variety, but I will just need surface. So this is nice and down to earth. I say Z in X is a zero-dimensional subscheme. Let's take like a point. And then the length of Z, LZ, is defined as the dimension of the global sections of OZ. Okay. So the Hilbert scheme of endpoints, Xn, is a variety parameterizing zero-dimensional length n subschemes of X. Okay. So it is really like a moduli space. Okay. What you're parameterizing is not sheaves or lines, but here you're really just parameterizing these length n zero-dimensional subschemes. Okay, so length n points. So this Hilbert scheme of points is irreducible. It is smooth variety of dimension 2n. The 2n here again because this is a surface, so that's why it's a 2. It has a universal subscheme. So when you have moduli spaces, you want to know if they are fine and if there is a universal subscheme. This has represents the Hilbert functor, and it has a universal subscheme Zn, okay, which is lying in Xn. So this Hilbert scheme of endpoints cross X, and Zn is Cohen-Macaulay and of codimension 2. Okay, so what Shen Vial show is that under some conditions, so these conditions I didn't spell out, but these are conditions on the Chern classes of X. Under some conditions, X admits MCK. I mean, if X admits MCK, so that means if the surface admits MCK, say a K3 surface or a abelian surface, then the Hilbert scheme of points also admits MCK. Okay, so this takes care of the one of the cases of the hyperkaehler varieties, right? Because that is the Hilbert scheme of points. But I'm interested really in the nested Hilbert scheme of points. So what is the nested Hilbert scheme of points? So the nested Hilbert scheme of points, denoted x to the n comma n plus 1, is that I take these pairs xn comma xn plus 1, okay, where xn is an element in the Hilbert scheme of endpoints, and xn is a subscheme of xn plus 1. Okay, so xn is contained inside xn plus 1, and xn is a zero-dimensional length n scheme of X, and xn plus 1 is a zero-dimensional length n plus 1 scheme of X. Okay, and the important thing is that this is contained in but not equal to the product of X, the Hilbert scheme of endpoints on X times the Hilbert scheme of n plus 1 points on X. Okay, again the nested Hilbert scheme is smooth, and its dimension is 2n plus 2. By Illingsrud and Strom, you can show that actually you can think of the nested Hilbert scheme x to the n comma n plus 1 as the blow up of the Hilbert scheme of endpoints cross X along this universal subscheme. Okay, so we said that we have this universal subscheme, right, Zn. Okay, so we can think of the nested Hilbert scheme as being as blowing up the Hilbert scheme of points cross X along this universal subscheme Zn. Okay. Then the question is that does this nested Hilbert scheme admit MCK for any n? And the answer is yes, and this is joint work in progress with Robert Laterveer. And maybe I should not take too much more time, but basically the case of x12 and x23 was done by Shen Vial. And what Shen Vial did is they used this kind of result that that this is, you can write this as the blow up along this universal subscheme. they use that to show that these two had MCK. But then the question is, so what is their idea? Their idea is that if you take, let's say, a variety V, which admits MCK, W, a subvariety, which also admits MCK, if you blow up V along W, then this blow up will also admit an MCK. Okay, so they show this, and then they use this Ellingsrud-Ström result to conclude that, in fact, X12 and X23 will admit MCK. Okay, but this is very good. Then why didn't it happen for all? You know, I mean, why is it that n here is equal to 1 and n is equal to 2? What about n equals to 3 and so on? And the thing is that this universal subscheme in these cases is very easy. For n equals 1, the universal subscheme Z1 is just the diagonal. For n equals 2, this is just X12, okay, which is also smooth. So it's very easy to show. But then as you get for n equals 3 onwards, this is actually Cohen-Macaulay. It is no longer smooth. So you want an equivalent result of Shen-Vial, which shows that if you have something which is MCK, and then you blow up along something which probably has MCK, then the blow up also has MCK. But the issue is that this variety W here would be Zn, which from n equals 3 onwards is not smooth. So that doesn't work. So what we are trying to do is we want to know that supposing you have a variety which has MCK and you blow it up along a singular center. Okay, so that means that you cannot say anything about the center having MCK because it is singular. Can you still conclude that the blow up will have MCK? And we believe yes, but we need, I mean, a lot of technical conditions, and I didn't want to go through the proof. So thank you.